And welcome back to 16.1, where we're discussing the properties of solutions. In the last podcast, we took a look at several definitions as to when you're making a solution, whether or not something is saturated or unsaturated, miscible or immiscible. We also took a look at factors that that affect how fast dissolving takes place. In this particular podcast, we're going to take a look at the factors that affect the actual solubility, the amount of solute that can dissolve. Not necessarily the speed at which it dissolves, but how much can be dissolved. All right. So let's go ahead and change up colors. We'll go with an orange in this case. The first factor we want to talk about is temperature. Now, temperature has varying effects depending on the solute that you're adding to the solution. Taking a look at this diagram below, you'll notice that many compounds will actually increase their solubility with greater temperature. For example, sodium nitrate has a solubility of a little less than 80 grams per 100 grams of water at 0 degrees Celsius. However, as you heat that as it approaches 90 degrees Celsius, it's over 140. Potassium nitrate, which is in the purple, that actually starts at very, very low, well, I wouldn't say very low solubility, but it's under 20 grams per 100 grams of water at 0 degrees Celsius, and it skyrockets to about 150 once you get over 80 degrees Celsius. So that's going to be increasing by more than sevenfold over that 80 degree span. There are some substances, however, that actually lose solubility as you heat things up. For example, this ytterbium sulfate goes from a solubility somewhere around 45 to 50 at 0 degrees Celsius and plummets down to, looks like, somewhere around 7 grams per 100 grams of water at 90 degrees Celsius. So the effects of temperature is going to vary. Now, one of the big problems that we have in terms of industry with this fact is dealing with boiler systems and calcium compounds. Calcium compounds tend to decrease in solubility as they heat up. So consequently what happens is if you have a pipe, and this is going to be a cross section of a pipe, let's just make it going in this direction like this, as water is flowing through the pipe, it's carrying calcium compounds. Well, when you heat up that calcium compound, it actually starts to precipitate out. And over time, what ends up happening is those calcium compounds start to deposit themselves on the edges of the pipe, and it actually starts to close it up. In fact, you can have pipes that are darn near closed up by the deposit of these calcium compounds. Now, I want to say there's nothing you can do about this, but the problem is that they are less soluble in hotter water, and we need to be pumping hot water through pipes. So you're going to have to find some type of solution to this problem. Now, what I do in the classroom is periodically with my water distiller actually shut the water distiller down and then put an acid in there that will dissolve the calcium compounds and then drain it out, so it will in fact get rid of all this stuff. Let's see if we have an eraser. There we go. There's an eraser. And we can actually get rid of that and start clean. Now, in many applications, that's not usually possible. Sometimes you just got to replace the pipe. All right, but temperature has a big effect on solubility. The other interesting thing is that gases, let's go back to the pen. There we go. Gases tend to have higher solubility at lower temps. Cold water dissolves more gas than hot water. All right. Not that you necessarily have to memorize that, but it's an interesting phenomenon. Now, moving on. If you carefully cool down a solution, you can actually create what's called a supersaturated solution. Now, a saturated solution contains the maximum amount of solute. However, if you take a solution, let's just go with, let's go with that KBr, which is right here. At 80 degrees Celsius, you can dissolve about 100 grams of KBr in 100 grams of water. However, at say room temperature, right around 20 degrees Celsius, you're at about 65 to 70 grams. What can happen is, as you cool this thing down from this temperature to this temperature, this amount of that amount of KBr should crystallize. But in order to crystallize, you have to have some type of nucleation site. You have to have some organization and some place for these things to crystallize around. If you don't, and you don't disturb it, you can actually get that temperature to drop down without having those crystals come out. So you actually, even though you should only have about 60 or 70 grams of KBr in the solution, you can actually maintain 100 grams if you do not disturb it. In that case, you have what's called a supersaturated solution. Contains more than the maximum amount of solute at a given temperature. All right. Now we have a really nice dramatic demonstration that you can take a look at. We'll be doing that in class, and we'll also hopefully get a link up for you guys to take a look at online to watch a supersaturated solution coming out of supersaturation. All right, let's go ahead and move on down. Number 2. The other thing that affects solubility is pressure, particularly when you're dealing with gas solubility. Henry's law is going to show us, or actually quantify, the change in solubility that takes place at varying pressures. If you take a look at the initial solubility of a substance at a particular pressure, that is going to be related to the solubility at a second pressure. So for example, if we have a gas that has a solubility in water at 0.77 grams per liter at 3.5 atmospheres of pressure, what is its solubility in grams per liter at 1 atmosphere of pressure? All right. So what's going to happen if you set this up as S1 P1 equals S2 over P2? Your original solubility was 0.77. The original pressure was 3.5 atmospheres. We're going to be looking for the new solubility, S2, at our new pressure of 1 atmosphere. Now, of course, this 1 you would have to multiply over to the other side. Of course, dividing by 1 doesn't do anything, so we really don't have to move that anywhere. So therefore, S2 is going to equal 0.77 divided by 3.5, and I'm getting 0.22 grams per liter of being the new solubility. Now we're starting to run a little low on time. We're going to wrap this up very quickly in the next podcast. We'll talk about why pressure is going to affect the solubility. We'll use an example of pop bottles, which I'm sure everybody's had the experience with, and then we'll wrap up the second part of sample problem 16.1. We'll see you next time.